Right now, somewhere in Virginia, there's a data center pulling enough electricity off the grid to power tens of thousands of homes just to keep one AI model running around the clock. And less than 2 years ago, in a lab in California, a machine that used almost nothing in comparison finished a calculation that the fastest supercomputer on Earth would still be working on long after everyone watching this video is gone. For years, we were told these two machines belonged to completely different worlds. One builds the future of artificial intelligence. The other was a science experiment that was always 10 years away. That separation just cracked. And if what happened over the last 18 months actually holds up, it could change how the entire AI industry is built, powered, and paid for. Before we get into what changed, you need to understand exactly how big the problem is that everyone is trying to solve. In 2026, data centers around the world are on track to consume somewhere in the range of 500 to 560 terawatt hours of electricity, according to industry estimates compiled from Gartner and the International Energy Agency. That is a jump of over 20% in a single year. AI-specific servers, the ones running models like the one you might be using right now make up close to a third of all that power draw, and they are growing far faster than everything else combined. The IEA has reported that electricity use from AI-focused data centers alone jumped by around 50% in just 1 year. To put that in perspective, in parts of Virginia, data centers already account for over a quarter of all electricity used in the entire state, and regulators expect that number could climb past 40% by the end of the decade. In Ireland, data centers already eat up close to a third of the country's total power, and in Dublin specifically, some estimates put that number near 80%. This is not a small technical footnote. This is one of the biggest energy stories on the planet right now, and it is why the 5 biggest American tech companies are expected to spend somewhere around $700 billion this year alone just building out AI infrastructure. That is more money in 12 months than the entire economy of Switzerland produces in a year. So when researchers started talking seriously about a completely different kind of computer, one that could, in theory, solve certain problems using a fraction of the electricity, the tech industry did not just take notice. It got nervous. Because if that different kind of computer could actually do what today's AI chips do, even partly, it would rewrite the economics of the entire industry. But here's the part almost nobody explains clearly, and it's the part that actually matters. To understand whether that's really happening, you first have to understand what this new machine can and cannot do. And that story starts with a chip named after a tree. In December 2024, Google's quantum research team introduced a processor called Willow, and what made it different wasn't raw speed, it was something more fundamental: reliability. Quantum computers, unlike the phone or laptop you're using right now, don't store information in simple ones and zeros. They use particles that can exist in multiple states at once, something scientists call superposition. Imagine a coin spinning in the air. While it's spinning, it isn't heads or tails, it's both at the same time until it lands. A quantum bit, or qubit, works something like that spinning coin. That property is what lets quantum computers explore many possible answers to a problem simultaneously, instead of checking them one at a time like a normal computer does. The catch has always been that this spinning coin state is incredibly fragile. The tiniest vibration, the smallest bit of heat, and the whole thing collapses into noise and errors. For decades, that fragility was the wall nobody could get past. More qubits meant more errors, not fewer. Willow appears to have cracked that wall, at least in a lab setting. Google's engineers found that when they grouped physical qubits into larger and larger clusters, called logical qubits, the error rate didn't rise, it fell, roughly cutting in half every time the cluster size grew, moving from 3x3 grids to 5x5 to 7x7. Julian Kelly, who leads quantum hardware at Google, described error correction as the actual end game of quantum computing, the thing that has to work before anything else matters. This is what researchers call operating below threshold. And it's a big deal because it means, in principle, you can keep scaling the system up and get more reliable instead of less. Then in October 2025, Google published a follow-up result called Quantum Echoes in the journal Nature, claiming Willow completed a specific calculation about 13,000 times faster than the best estimate for a classical supercomputer doing the same job. IBM pushed back hard on that comparison, arguing the same task could actually be run on one of its own classical supercomputers in roughly 2.5 days, not the geological timescales Google implied. So even inside the industry, experts disagree on exactly how big this gap really is. What almost nobody disputes, though, is that the error correction breakthrough itself is real. And Google isn't the only company betting on this future, or even betting on the same kind of machine. Microsoft has spent nearly 2 decades pursuing a completely different approach called topological qubits, built around exotic particles known as Majorana zero modes, which are theorized to store quantum information in a way that's naturally protected from the noise that plagues other designs. In February 2025, Microsoft unveiled its first chip using this approach, called Majorana 1, and by June 2026, at its Build Developer Conference, it had followed up with Majorana 2, a chip that used a lead-based superconductor instead of aluminum and reportedly pushed qubit stability up roughly 1,000 times over the original. Microsoft's physicist Chetan Nayak called it a major leap in that critical stability metric, and the company says the progress lets it target a working fault-tolerant prototype by 2029, 4 years earlier than its original 2033 goal. But here's where this gets genuinely uncertain rather than just a marketing story. Physicists outside Microsoft, including Henry Legg at the University of St. Andrews, have publicly questioned whether the company has actually proven it has a real topological qubit at all, pointing out that Microsoft's published data leaves out one of the two measurement types scientists say are needed to confirm it. This is a field with a history of retracted claims, and that history is exactly why outside physicists are demanding a higher bar of proof before accepting the announcement at face value. So even the next generation of quantum hardware is genuinely contested science, not a settled fact. What's still very much up for debate is what any of this actually means for the rest of us. And that debate is exactly where this story gets complicated. Because here's the question that matters more than any of the headlines. Does a quantum computer that can beat a supercomputer at one narrow calculation mean it can replace the chips running ChatGPT, Gemini, or any other AI model you use every day? The honest answer, based on what people actually building this technology are saying, is no, not even close, and probably not for a very long time. Quantum computers are extraordinary at a specific category of problem, simulating complex molecules, optimizing huge logistics networks, cracking certain types of encryption. Jensen Huang, a senior research scientist at Google Quantum AI, has pointed out that simulating quantum mechanical systems for things like new drugs or new materials is a job that piling on more ordinary chips simply cannot solve no matter how many you use, because the problem is fundamentally the wrong shape for that kind of hardware. But training and running the large language models behind today's AI products is a different kind of math entirely, built around massive parallel matrix operations. That happens to be exactly what graphics chips, the kind Nvidia builds by the millions, are extremely good at. So the two technologies aren't really competing for the same job. They're built for different jobs that just happen to live in the same industry. But if that's true, why has the world's most valuable chip company suddenly started acting like quantum computing is a threat worth taking seriously? There's also a second reason companies and governments are taking this so seriously, and it has nothing to do with training AI models. It has to do with breaking the locks that protect almost everything online today. Most of the encryption securing your bank account, your medical records, and government systems relies on math problems that are essentially impossible for a normal computer to solve in a reasonable amount of time. But a sufficiently powerful quantum computer, in theory, could solve them. That risk is serious enough that the National Institute of Standards and Technology finalized its first quantum-resistant encryption standards back in August 2024. And by 2026, companies like Cloudflare reported that more than 65% of the traffic on their network was already protected using this new quantum-resistant encryption. Federal agencies have been given until 2030 to phase out the old vulnerable systems entirely, and the concern driving that timeline is something security researchers call harvest now, decrypt later. The idea that someone could be quietly collecting encrypted data today, simply waiting for the day a quantum computer is powerful enough to unlock it. Most researchers place that moment somewhere between 2033 and 2037, which is a completely different, and arguably more urgent, storyline than anything happening with AI data centers. It's a reminder that the real impact of this technology might show up somewhere you weren't even watching. But back to the data center question, because that's where the story keeps circling, and it's about to take its most surprising turn. That brings us to one of the most interesting reversals in recent tech history. At the start of 2025, Nvidia CEO Jensen Huang was publicly dismissive about quantum computing, suggesting useful, practical quantum machines might be 15 to 30 years away. That single comment reportedly wiped billions off the market value of publicly traded quantum companies within days. Then, within months, Huang did something he rarely does. He walked it back. By June 2025, he was describing quantum computing as approaching what he called an inflection point. And by April 2026, Nvidia wasn't just talking about quantum computing. It was actively building for it, releasing a set of open-source AI tools called Ising, designed specifically to help stabilize and control fragile quantum systems using artificial intelligence. Huang's framing was that AI would essentially become the operating system running underneath quantum machines, turning unreliable qubits into something scalable and dependable. When that announcement landed, quantum stocks like IonQ jumped more than 50% in a matter of weeks. Though it's worth being honest here, those same stocks were still trading well below their highs from the year before, which tells you this is still a volatile speculative corner of the market, not a settled one. What Huang's pivot actually reveals is the real shape of where this is heading, and it's a lot less dramatic than quantum kills the data center. Patrick Moorhead, an analyst at Moore Insights and Strategy who tracks this industry closely, has described quantum processors not as a replacement for AI infrastructure, but as a kind of specialized add-on, a hybrid tool that still needs a powerful classical computer sitting right next to it to actually be useful. Nvidia's own software platform for this, called Q2Q, is built entirely around that hybrid idea. Quantum processors handling the narrow slice of problems they're good at, while ordinary GPU-powered systems handle everything else, including basically all of today's AI training. But that promise only applies once these machines are actually doing useful, large-scale work. And that's a much bigger if than most headlines let on. So if quantum computers are joining data centers rather than replacing them, does that actually solve the energy crisis we started with? That's where the story takes its most surprising turn yet, because quantum computers are not free. In fact, in some very real ways, they might end up being demanding in their own right. Most of today's leading quantum chips, including Google's Willow, have to be cooled to temperatures colder than deep space, using a piece of equipment called a dilution refrigerator. A single one of these machines can cost anywhere from $300,000 to $3 million, and it typically draws 25 to 50 kilowatts of power continuously, which is roughly the same as running 25 household air conditioners nonstop just to keep a few hundred qubits cold enough to function. Once you add control electronics, facility overhead, and maintenance, running one full quantum system can cost well over $10 million a year. And there's an even stranger bottleneck hiding underneath that number. Many of these refrigerators depend on a rare isotope called helium-3, which doesn't come from natural gas wells the way ordinary helium does. It's a byproduct of the slow radioactive decay of tritium inside nuclear weapons stockpiles. It currently costs somewhere between $1,900 and $2,600 per liter. As more quantum computers get built, more of them are going to need this genuinely scarce material, and there's no easy way to simply manufacture more of it on demand. A study led by David McCollum, a distinguished scientist at Oak Ridge National Laboratory and a joint faculty member at the University of Tennessee's Energy Policy Center, looked at what happens as this technology tries to scale up commercially. The findings were sobering. Large-scale, fault-tolerant quantum computers, the kind capable of outperforming classical machines on real business problems, are not expected to become commercially available until the late 2030s at the earliest, and when they do arrive at scale, they could create substantial new electricity demand of their own, layered on top of everything AI is already using, along with meaningful water consumption for cooling. So the machine some people are calling a data center killer might, at true commercial scale, end up needing its own dedicated power supply and its own fragile supply chain. That is a very different picture from the quantum saves the planet narrative you might see in a thumbnail. To be fair, not every approach shares this problem. Companies like D-Wave build a different, more limited style of quantum machine called an annular, which is used for narrower optimization problems and runs on roughly the same 25 kilowatts as a single dilution refrigerator, without needing the same scale of error correction. And some analysts argue that because certain quantum algorithms can solve specific problems in dramatically fewer steps, the energy used per useful answer could still end up lower than a classical approach, even with all this overhead. Experts genuinely differ on how that balance nets out once you're talking about millions of qubits instead of a few hundred. So where does that leave the next few years, the part that actually affects decisions being made right now? The honest, unglamorous answer is, not with quantum computers replacing AI data centers, but with the two slowly starting to merge. Companies like AWS, Google, IBM, and Microsoft have all expanded pay-as-you-go access to quantum processors through the cloud in 2026, meaning a researcher can now rent time on a quantum chip the same way they'd rent cloud storage without buying tens of millions of dollars of hardware themselves. IBM has been pushing forward with a newer chip called Nighthawk, built around 120 physical qubits, as part of its roadmap toward practical fault tolerance later this decade, while Quantinuum, one of the more advanced players in the space, filed paperwork in the last year to go public. But researchers at Riverlane, a UK-based company that builds quantum error correction software, have published projections suggesting that truly practical, fault-tolerant quantum computing will require processors running tens of thousands, potentially millions, of physical qubits. Current hardware, even Willow's and Majorana's most advanced descendants, is still a long way from that number. As one industry analysis put it plainly, the milestones of the last 2 years are validating the path forward, not completing the journey. That single sentence might be the most accurate summary of where this entire field actually stands. If you're finding this kind of grounded, no-hype breakdown useful, it genuinely helps the channel if you hit subscribe. because we're going to keep tracking exactly how this plays out as the real numbers come in, not the headlines. So let's bring this all the way back to that data center in Virginia and that lab result from Google. The title of this video asks whether a quantum breakthrough could kill AI data centers. And after everything you've just heard, you can probably guess the real answer isn't a clean yes or no. It's something more useful than that. Quantum computing in 2026 is real. It's advancing faster than almost anyone predicted even 2 years ago, and companies that once dismissed it, including Nvidia, are now racing to build around it instead of ignoring it. But it is not a replacement technology, and it comes with its own costs, its own rare materials, and its own unresolved scientific arguments. It's a specialist, arriving to sit beside the general-purpose machines that already run the world's AI, taking on the narrow set of problems those machines were never built to solve efficiently, while classical chips keep doing what they already do well. The AI data center boom isn't going away because of quantum computing. If anything, based on what companies like Nvidia, Google, Microsoft, and IBM are actually building right now, quantum processors are on track to become one more rack in that same data center, not its replacement. The breakthrough that matters here isn't a machine that kills an industry. It's two industries that spent a decade acting like strangers, finally realizing they need to be built in the same room.